Hey, BOT 105 students, it's me, Stephanie, and I'm here to talk about the scientific method. We're going to talk about a couple versions of the scientific method, but we're going to focus on the Western scientific method. I'm going to explain what that means, but we're going to talk about what the hypothetico-deductive method is, and we're going to break it down. This particular lecture video doesn't have a ton to do with the other two lecture videos of this week directly, but I promise we're going to bring it all together in lab, and this video is still super important. So here are our lecture outcomes as questions. Is there only one version of the scientific method? The second one, what are the types of questions asked by scientists? And number 3, what are the particular steps of the hypothetico-deductive approach to scientific reasoning? Here's a list of the vocabulary we always like to provide. Please feel free here to pause and write these down. Moving on. Starting with the first lecture outcome question. Is there only one version of the scientific method? This is a critical thinking course, and I want you to be aware of the fact that the scientific method is, in fact, more than one method. And in fact, scientific methodologies themselves have been evolving for centuries. So no, it depends on how narrowly one defines the scientific method, though. So traditional ecological knowledge, or TEK, we've talked about before in BOT 105, or indigenous science, is a part of every culture and is characterized by careful observation, replication over time, namely thousands of years in one location, and a blending of these methods with spiritual practices. So an example would be the extremely important and vast knowledge indigenous peoples have of wildfires. And this is, of course, extremely important information for everyone. And spirituality here may have been important because maybe it wouldn't have gotten passed down for so many generations if it wasn't so meaningful and important. Western science includes careful observation and replication, so both of those. They share with traditional ecological knowledge, both of those traits. And further steps, but it is not deliberately blended with spiritual practices. Western science uses logical approaches like inductive and deductive reasoning, which we're going to talk about, for assessing the likelihood that an argument's conclusion is true. These approaches were formalized by Western philosophers, hence Western science. And really, logic, what we're talking about, logic in the sense that we can reduce the parts of a statement or an argument into symbolic representatives, which is actually a philosophical thing. And so we call, those with the most knowledge in our field, they earn a PhD, a Doctor of Philosophy in Biology, or a Doctor of Philosophy in Music. An argument is composed of two parts. Premises and conclusion. Premises are statements that are offered as evidence or a reason for accepting the conclusion. And a conclusion is a statement that the premises are intended to prove or support. So premises and conclusions are dependent on each other, even in their sort of definitions here. And let's expand on that a little bit. Who does a lot of arguing? Lawyers. They might say, my defendant was at home with their mom at the time, and therefore they are innocent. Well, my defendant was at home with their mom at the time is a statement that is offering evidence for accepting the next thing that's about to be said, which is that my defendant is innocent. That would be the conclusion. That was supported by this evidence that they were at home with their mom. So more about arguments. There are two types of arguments, and sort of starting with deductive, actually, on the right. Deductive, in a nutshell, a deductive argument is one that attempts to prove the conclusion. This is ideal scientifically. A deductive approach, if it can be used, is stronger for assessing the validity of a conclusion. We'll talk about this more. In general, deductive arguments are more exploratory than inductive arguments, which an inductive argument is a conclusion, is one where the conclusion is probable or likely, especially sort of based on the statements. So the problem with inductive arguments is that they could be subjective. A classic example of an inductive argument is the coin I pulled out of this bag is a penny. The next coin I pull out of this bag is a penny. A third coin I pull out of this bag is also a penny. Therefore, all of the coins in this bag are pennies. So that conclusion that all of the coins in the bag are pennies was sort of what we would call an inductive leap here. Even though the previous statements, the first statements were true, inductive reasoning allowed for the conclusion to be false. Since foliose means leaf-like, since foliose algae are missing from the high intertidal zone, and since limpets eat foliose algae, limpets are the reason that foliose algae are absent from the high intertidal zone. Okay, so we've got these statements. Foliose algae are missing from the high intertidal zone. Okay, that might be true. It is true, actually. And limpets eat foliose algae. Yes, this is also true. But then is it a sound conclusion to say that limpets are the reason that foliose algae are absent from the high intertidal zone? So, in other words, is there just a correlation here? Or is one causing the other? Okay. So the second lecture outcome. What are the two types of questions asked by scientists? One, is there a pattern to the observations? And two, why is this pattern of observations occurring? Or in other words, what are the mechanisms producing the pattern that we're observing? And really, when we do see a pattern, we then ask the question, well, is it correlation or is it causation? Correlation is types of variables, each described by a set of observations that always occur together, but one does not cause the other. So a classic example that I like to give you, ice cream sales are high on the same days that surfing rates are high. Therefore, can we conclude that eating ice cream causes surfing? Well, no, there might be a correlation, and that would be good weather, but one does not cause the other. So causation is when one variable does directly affect another variable. Number 3, what are the particular steps of the hypothetico-deductive approach to scientific reasoning? And this is what we're going to expand on quite a bit right now using a real example. So hypothetico-deductive reasoning, the whole idea is to falsify a hypothesis, actually. You might think that sounds wrong. The whole point should be to prove a hypothesis. No, actually, the whole point is to falsify one, because that's actually stronger than proving one. Because proving one might actually be inductive. So first we would start with observations. We're describing this puzzle or this pattern that we see, and it's really important to do that accurately, right? So related to that previous argument, I observed that there are no leafy algae above the intertidal zone. And so maybe a possible explanation for that would be the observation that limpets live above the zone as well. And so one model for the observation of there being no algae above the intertidal zone, one model for that is that limpets eat them above the intertidal zone. Okay, but there could be other models. That's what is important here. There's not just one model to explain an observation necessarily. And so we're going to go through these, each of these steps one by one. Observations, model, hypothesis, and a null hypothesis. We're going to talk about the difference between those, and a test. Okay, starting with observations. Observations, maybe a description, a pattern, a puzzle, a problem. These are observational studies that need to be done precisely. They need to be done well. One needs to take careful measurements or at least studies, and you need to make sure that need to make sure that they are observing it in all ways that one can think of. Thinking outside of the box and trying to look at a system from a different angle is always useful to complete an observational study. And this is so important because it is the basis for the rest of the scientific method. So let's talk about this real-life example of the rocky intertidal zone and foliose algae. So foliose, again, is sort of a leafy algae, and just think of sort of a leafy seaweed. So here's a figure that shows what this is sort of the angle of the Earth in this picture here, in this diagram. And these represent grazers, maybe potential limpets, things that feed on the algae. And then this is the actual algae down here in black. We've got low water level represented here, and then the limit of these foliose algae right here. Okay. Now in this figure, the x-axis is height above the chart datum. So essentially just the height within the intertidal zone. So lower height would be down here and higher height would be over here on the right. And then the y-axes are these two lines, or are represented by these two lines. The solid line here is the algae, density of algae. And then the dotted line here is the density of the grazers. And notice that with increasing height, there are decreasing algae and increasing grazers to a certain point. Moving on. Or one might ask now, is this correlation between grazers and foliose algae? Well, here's what other folks did. They looked and made more observations of this intertidal zone, and they looked in great detail. They looked at the temperature variation. They noticed that, it's not like limpets are the only difference between the upper and the lower intertidal zone, essentially. There's a huge temperature variation. It's warmer in higher zones. And maybe that has to do with the amount of sunlight, which is also increased in higher intertidal zones. There's also a higher salinity variation in higher zones, higher time exposed to air, and lower competition. Okay. So all of these factors are influenced by the exact location an organism ends up in the intertidal zone. Here's what some of the players of this system look like. Here are some examples of those foliose algae that we're talking about. These are really diverse pictures here. Okay, so the next step in the hypothetico-deductive reasoning is to produce models. So if you're focusing on whether or not the pattern of your observations in the rocky intertidal zone is common, then come up with a summary, come up with a model protocol and for your observations, and compare your model to a similar study or repeat your work at another place or time to make sure that there is some consistency and it's not just a one-off what you're seeing. But if you want to focus on why certain algae and invertebrates only occur in particular intertidal zones, then you need to get creative and come up with multiple explanations, which are models in this case, that could each account for your observations. So you need to come up with multiple potential reasons that might explain the observation that you're seeing. And this is one of the most exciting, creative parts of doing science, of course. So these models, they can be verbal, written, illustrated, mathematical. Moving on. Here are some intertidal models from an example in 1991 by Underwood. Regarding this observation and question, why do certain algae and invertebrates only occur in particular intertidal zones? And so we're striving to find this hypothesis and create a study that produces data that clearly supports a hypothesis. We're not trying to devise a study that produces data to support your favorite idea or anything. We need to kind of equally test all models, all ideas, and frame our hypotheses in a way that they can be examined by a study. So here are 4 different potential models that could explain why certain algae and invertebrates only occur in particular intertidal zones. Maybe there is dispersal limitation on the part of the algae, of the alga, rather. Maybe another model is high intertidal physical conditions are beyond the physiological tolerances of foliose algae. All right, that sounds logical as well. Model 3 is high intertidal grazers of foliose algae are present. So these grazers like limpets and other invertebrates. Model 4, high intertidal algal crusts competitively displace foliose algae. So algal crusts are these sort of very flat, crustose algal organisms that grow directly on the rocks and are less sort of 3-dimensional than foliose algae, which are more leafy. So here are some of the players, some of the other players. By algal propagules, really, what we're talking about in a nutshell are spores, different sort of types of spores. And here are what they might be produced in, right here. And here's maybe a close-up of a certain type of spore. Limpets, these might be grazers. They sort of look like that. And this red or brown or dark purple stuff that's on top of this rock is actually an algal crust. So this is a living algal organism that just has this crustose form that it's sort of oppressed itself completely to the rock. Sorry, Frank, he would have done a much better explanation of that. A hypothesis is generated by one of these models. A model that is explaining our question or observation. And you need to frame your hypothesis in a way that it can be studied. So are testable predictions about some response variable, some dependent variable, given the conditions of the independent variable. The resulting data must clearly support or not support the hypothesis. We can't have any gray areas or iffy places in the middle. We need to have strong support of either support or not support of a hypothesis. So back to our example, the hypothesis for, let's say, that first model, the dispersal limitation model. So maybe there are no propagules of the foliose algae that will occur in the high intertidal, but they will be found in the low intertidal. If so, then that would sort of lead one to believe that the reason why foliose algae is not making it above the intertidal zone is because they are limited by dispersal, if there were no spores up there. And so you could imagine to design a study here that is a study here is something that has been set up to capture algal propagules in both locations. So maybe something that these spores will attach to in both locations, the high and the low intertidal zone. Here, the y variable, which is our response variable, is the number of propagules. The x variable is the intertidal zone, high or low. And so is the number of propagules dependent on location in the intertidal zone? So talking about what a null hypothesis is. A null hypothesis is sort of something different from what you are possibly thinking in your study, right? A null hypothesis is when neither of your variables are connected to each other, or the alternative hypothesis to the one that you are interested in. So H1 here stands for alternative hypothesis, and A is greater than B here. In our example here, A is spores in the low intertidal zone, and B is spores in the high intertidal zone. So we had a hypothesis that there would be more spores in the low intertidal zone than spores in the high intertidal zone if they are dispersal limited. So the null hypothesis, which is represented by H0, would be shown if our results showed that the spores in the low intertidal zone were equal to the spores in the high intertidal zone, or if we found that there were more spores in the high intertidal zone than there were in the low intertidal zone. And we cannot prove the alternative hypothesis with an inductionist approach. That's not what this is about. Instead, we're trying to disprove a hypothesis, and here, namely, we're trying to, or we're interested in seeing if we will disprove the null hypothesis. If so, then we would end up with support for our alternative hypothesis, not proof of the alternative hypothesis, but support for it. Okay. Confidence in the explanatory power of a model grows as the null hypothesis continues to be rejected. Okay. So the logical null hypothesis for our example here for the model of dispersal limitation. The null hypothesis, H0, for our alternative hypothesis, which we already talked about, is if algae are capable of dispersing to the upper intertidal, then the same number of propagules will occur in high and low intertidal plots, or there will be more propagules in high intertidal plots. Okay. And here again, just to remind you, same variables. Same exact variables, just a different hypothesis. And so this is the system of the hypothetico-deductive scientific method. So the first step here was observations. No foliose algae in the high intertidal zone. This is something that was noticed and folks had questions about. Well, one of the models was that they're absent from the high intertidal zone because their spores can't reach the high zone. Or in other words, they are limited by their dispersal ability. Well, if that is the case, if they are absent from the high intertidal zone because their spores can't reach the high zone, then there will be no spores found in the high zone. But there will be spores in the low zone. So you still have to check both, and that's what we have been talking about. The null hypothesis is just as important as your sort of main hypothesis, known as the alternative hypothesis. The null hypothesis in our example was the number of spores found in each zone will be the same, or there will be more spores in the high intertidal zone than the low zone. In this case, the study could place recruitment tiles in each zone for several months to see if microscopic examination of those tiles revealed any spores. That would be the test. And if we retained the null hypothesis, right? So if we did find spores on these microscopic, or on these tiles, these recruitment tiles, after examining them, if we did find them in the upper zone, well, then we would have to think of what other model could explain the lack of algae. We would kind of have to go back. If we rejected the null hypothesis, so in other words, if there were no spores found in the upper intertidal zone, then we would need to continue this process. Notice that there's no end here. We would then ask, well, is there another model that also explains the lack of algae? Are there two models acting together? That might be another question. Or maybe another question would be, can we figure out why their spores are incompatible with the high intertidal zone? There's going to be a continuation of questions, and that's one really special thing about the scientific method as well.